Good morning, all of you. Welcome to Sri Jayendra Rank Zone. So far, we have completed D block elements. Now we are going to do F block elements in this class. So in this session, we are going to do F block elements. D and F block. The name we have written is D and F block as in the textbook. But now in this class, we are going to do completely about F block elements. That is inner transition elements. Inner transition elements. So far, we have completed transition elements, and now we are going to do inner transition elements. So let us see what are inner transition elements. So the inner transition elements, they are also called as F block elements. Inner transition elements are also called as F block elements because the differentiating electron enters into the F orbital. The elements in which the differentiating electron enters into n-2 F orbital of anti-penultimate shell are called as F block elements. So in D block elements, we have seen n-1 D shell, and that is penultimate shell. Penultimate shell means the shell before valence shell is called penultimate shell. Penultimate shell means the shell before valence shell. Now here n-2 F orbital of anti-penultimate shell. The shell before penultimate shell are called as anti-penultimate shell. So the elements in which the differentiating electron enters into n-2 F orbital of anti-penultimate shell are called as F block elements. These are called as F block elements, and these are placed separately in the periodic table. This we already know. And these have three outer shells incomplete. Three outer shells, that is n-2 is incomplete, n-2 F orbital is incomplete, n-1 D orbital is also incomplete, and ns1 or 2 also incomplete. So it has totally three orbitals incomplete. So the general electronic configuration is n-2 F1 to 14. Since F orbital has 7 suborbitals, it can take maximum 14 electrons. D can take maximum 10 electrons. This already we know. So n-2 F1 to 14, n-1 D1 R0. Here very important. D either 1 or 0, and it is ns2. So this is the general outermost configuration of F orbital. Then general outermost configuration of electronic configuration of F orbital, that is inner transition elements, F block elements. So the elements in which the differentiating electron enters n-2 F orbital of anti-penultimate shell are called as F block elements. Continuation. Now this 4F series, F block elements consisting of mainly two series. One is 4F series, another is 5F series. So 4F series are called as, so F block elements consisting of only 4F series as well as 5F series. 4F series consisting of 14 elements, and 5F series also consisting of 14 elements each. So 14 elements. These are placed separate in the periodic table. These are placed separate in the periodic table. So this 4F series, if the differentiating electron occupy 4F subshell, the valence electron of the element occupy 4F subshell and occur rarely in its crust, so called as rare H. So that's why the elements of lanthanides. So 4F series is called as what? Lanthanides. These are called lanthanides, and these are also called as rare earths. Rare earths means these are not found usually in nature. Next, these are called as actinides, lanthanides and actinides. So total there are 28 elements in F block elements. F block. So the differentiating electron occupy 4F subshell and occur rarely, rarely in H crust. So they are called as rare H. The general electronic configuration of lanthanides. So these are also called as lanthanides. 4F series elements are also called as lanthanides. 4F series elements are called as lanthanides. So the general electronic configuration of lanthanides is 6s2, 5d0r1, 4f1 to 14, 4f series. So that's a 4f1 to 14. This is n-2, that is 4, n-1, that is 5, n is equal to 6. The following table gives the electronic configuration of lanthanides in ground state and in +3 oxygen state. Usually they form +3 oxygen states. So all lanthanides. So the next slides we are going to discuss all these things. Let us see the configuration. So what are the elements I have told you? So lanthanum is belonging to D block element, but still it is placed in F block element. That's why it is D1, D1, because these elements properties are more similar to inner transit elements, but it's better to count from the cerium only. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So after lanthanum, total 14 elements. So from cerium to lutetium, these are all total 14 elements. These are all called as F block elements. So they have lanthanum, as I told you, the valence electron is entering 5d1 6s2. There is no F orbital. And cerium, 5d1 6s2 plus 3 state means all the 3 electrons will be 0. So it becomes 4f0. Next, cerium. Atomic number is 58. Xenon 4f2 6s2. Xenon 4f2 6s2. Xenon is 54. So 54 plus 4, 58. And there is no d orbital in cerium. That's why it is called as F block elements. And after removing 3 electrons, it becomes 4f1. Next, praseodymium. So these 4f and 5f series elements are very important. So praseodymium, it is atomic number 59, 4f3 6s2, and in plus 3 state it is 4f3. And promothium, promothium, that is 61, 4f4, that is plus 3 state, and 4f5, 5s 6s2, and samarium, 4f6, 6s2, 4f5. Europium, here europium is important. Europium, 4f7, 6s2. 4f7, 6s2 is europium. And plus 3 state, it is 2 electrons from s orbital is removed. After that, 1 electron is removed from f orbital. Then it becomes xenon 4f6. Europium, why I have underlined? Because it is half filled. Half filled means 4f7 half filled and complete filled orbitals. So that's why it has unusual stability. Unusual stability due to half filled and completely filled. Unusual stability. Even this also lanthanum, uh, unusual stability. Next we have gadolinium 64, 4f7, 5d1 6s2, and this is again 4f7. So gadolinium plus 3 has unusual stability. GD plus 3 state means it is losing 3 electrons. Gadolinium has unusual stability because it is having half filled. It is half filled f orbitals. Half filled F orbitals. So half filled and complete filled means their ionization enthalpies will change from the successors and the predecessors. Next, terbium 4f9 6s2. Next we have, so this is also 4f7, you can see here. And dysprosium, gadolinium, europium, you have to remember definitely. Dysprosium 66, 4f10, 6s2, 4f9. And holmium, it is 67, 4f11, 6s2. And erbium, thallium, ytterbium, lutetium. Lutetium, again, you have to remember lutetium, ytterbium. Ytterbium and lutetium, because they have 4f14 configuration. 4f14, 4f14 means completely filled. Completely filled means unusual stability. So completely filled F orbitals. Half filled F orbitals, completely filled F orbitals. Completely filled F orbitals. So please note down all these things. So completely filled F orbitals and half filled F orbitals. Next continuation. So these are the elements. In this total 5 elements are important. Europium, gadolinium, ytterbium, lutetium due to half filled and complete filled in their ground state configuration as well as in plus 3 state configuration. This is not in plus 3. So in this is ground state configuration 4f7 6s2. So due to half filled f orbital and completely filled s orbital. And here also half completely filled f orbital as well as s orbital. And here lutetium also completely filled f orbital and completely filled s orbital, and half filled, not even half filled. So it is 5d1 again, more stable state. And plus 3 state, it is 4f14, 4f7. So these two are 4f0. So these things you have to be thorough with this. So europium, gadolinium, ytterbium, lutetium, all these 4 elements. What is the atomic number of europium? 63, gadolinium 64, ytterbium 70, lutetium 71. Next continuation. So what are the things you have to remember? Please note down in your classwork, whichever I have underlined. The atomic radii and ionic radii of lanthanides, very, very important, decreases steadily with the increase in atomic number. This is known as lanthanide contraction. The atomic radii and ionic radii of lanthanides decreases steadily with increase in atomic number. So here decrease is very important. So due to the poor shielding effect of F electrons, due to the poor shielding effect of F electrons, what happens? The outer electrons. Actually, what is the outer electrons it has? So it has n minus 2, F1 to 14, n minus 1, D0 R1, 1 R0, and ns2. This is the configuration, right? So the outer electrons, that is ns electrons, is not shielded by f orbitals, due to which what happens, the outer electrons will come closer to nucleus, due to which what happens, contraction takes place, and this contraction is known as lanthanide contraction, and it is formed due to the poor shielding effect of f electrons, the poor shielding effect of F electrons. The variation of atomic size with atomic number of lanthanides is given by the following graph. That graph is very important. Almost all the elements have similar atomic radius because of lanthanide contraction. So you can just see, just it is from 2.7 to 2.25. So it's very small, minute gap. So that is called atomic radius versus atomic number. As the atomic number increases 58, 59, 60, 61, 62, the atomic radius decreases, that is 2.7, 2.67, 2.64, 2.52, 2.59, and maximum it is up to 2.25. And this is called atomic radius was atomic number for lanthanides, that is 4F series. Next continuation. Consequence of lanthanide contraction. Definitely they'll ask this question in the entrance exam. What are the main consequences of lanthanide contraction? So which of the following is the consequence of lanthanide contraction? Which of the following is the consequence of lanthanide contraction? Or they'll say, which of the following is correct regarding the lanthanide contraction? Which of the following is correct regarding lanthanide contraction? So, from lanthanum, that is La plus 3, to lutetium, Lu plus 3, the ionic radius changes from 106 picometers to 85 picometers. Since all the members have almost similar size, it is difficult to separate from their mixture. So, this is the first effect. Due to the lanthanide contraction, first is what? The ionic radius is almost similar from lanthanum to lutetium plus 3. So ionic radius of La plus 3 to lutetium plus 3. The ionic radius or atomic radius is almost similar. So it is very difficult to separate from their mixture. Second one, the small average decrease. The small average decrease in atomic size is responsible for small decrease in electronegativity and standard oxidation potential of, this is SOP, is called standard oxidation potential of lanthanides. Next, very second point, third point it is actually, the basic character of oxides and hydroxides decreases from lanthanum hydroxide to lutetium hydroxide. So as we move from left to right, what happens? The metallic character decreases, so basic character also decreases. So the basic character of oxides or hydroxides decreases from lanthanum to lutetium. This point is also important. Based on this point also, they can frame a question. So due to lanthanide contraction, there is the ionic radius and atomic size are almost similar for lanthanides. Next continuation. Definitely you'll get a question based on lanthanide contraction. Due to lanthanide contraction, atomic area of 4D and 5D series are similar. 4D and 5D series are similar. So what are the elements of 4D? Zirconium and hafnium have similar size. Niobium and tantalum is similar size. Molybdenum and tungsten have similar size because of their lanthanide contraction. That is due to poor shielding. In this case, what happens? Due to poor shielding effect of d electrons. Due to poor shielding effect of d electrons. So that contraction is also called as lanthanide contraction. So d electrons, f electrons shielding effect is considered to be lanthanide contraction. So lanthanide will say the name because it is mostly for lanthanides. So zirconium, hafnium, niobium, thallium, tantalum, molybdenum, tungsten, all will have same atomic radii. That is, you can see the values almost is absolutely same, just only small difference. Next continuation. Now, what are the common oxidation states of lanthanides. The most common and stable oxidation state of lanthanides is plus 3 only. Plus 3 means maximum it can lose 3 electrons. The corresponds to the use of two outermost electrons along with one inner electron, that is F electron. The inner electron is used is a 5d electron or one of the 4f electrons if no 5d electrons are present. So in some elements we have seen 5d elements also. First electron will go from S, two electrons will go from S orbital, that is 4, that is 6s orbital, and next one electron we may go from 5d if 5d electron is having, if the element is having one electron in d orbital. Otherwise, it will go for 4f orbital. So two electrons from a 6s orbital and one electron from 4f orbital. So usually the most common oxidation state of lanthanides is plus 3. So in lanthanum, gadolinium, lutetium, it is 5d electron or one of the 4f electrons if no 5d electrons is present. That is remaining elements, electron is going from f orbital. So in which elements electron is going from d orbital, third electron, that is lanthanum, gadolinium and lutetium. These three elements very, very important. Please note it down. From the three elements, these three elements, two electrons from s orbital and one electron from d orbital. No electron from f orbital will go off. Whereas in this, as there is no d electron, so f electron, one electron will be lost from f orbital. Next continuation. Some elements exhibit also plus 4 oxygen state, plus 4 oxidation state. For example, chromathium plus 4, cerium plus 4, terbium plus 4, dysmorium plus 4 exist in aqueous solution. Some elements exhibit even plus 2 oxidation states also, like samarium plus 2, europium plus 2, 4, telmiston plus 2 and ytterbium plus 2 due to their half-filled, fully filled and noble gas configuration. So why they are exhibiting plus 2 also? Due to their half-filled, completely filled noble gas configuration. So in this also, electronic configuration of F elements is very, very important. Electronic configuration is most important. So you have to be thorough with all the numbers. Electronic configuration is very, very important. From this electronic configuration only, you can understand whether they can form plus 2, plus 3, or plus 4. Almost all the elements will form plus 3 oxygens, plus 3 oxygen state. In addition to this, some elements may form plus 4. What are those elements? Chromathium, cerium, terbium, dysmorium. And some elements will form plus 2 also. What are those elements? That is samarium, europium, uh, Tm plus 2, Yb plus 2, ytterbium plus 2, tungsten plus 2. So all these elements are very, very important. So please note it down. So these are the oxidation states of lanthanides. Now coming to general properties or general characteristics of lanthanides. All lanthanides are soft metals with silvery white color. Very, very important. They are having all lanthanides are soft metals with silvery white color. They tarnish rapidly by air. Tarnish means getting rusting. With increasing atomic number, the hardness of these metals also increases. The melting points of lanthanides ranges from 1000 to 1200 kelvins, but samarium melts at 1623 kelvins, unusual melting point for samarium. Lanthanides have low values of first and second ionization energies, which are closer to alkaline earth metals, especially to calcium. So they have low value of first and second ionization enthalpies, which are closer to alkaline earth metals, especially to calcium. Continuation. All the general properties are important. On account of fairly low ionization energy and large atomic size, lanthanides behaves as strong electropositive metals. So these are strongly electropositive metals, but as their availability is very, very less, so that's why you will not find many reactions lanthanides. They do not have much tendency to form complexes due to low charge density because of their large size. Lutetium plus 3 is smaller in size, can only form complex. So which lanthanide will form complex compound? Only lutetium, except lutetium. Remaining all other elements in F block elements do not form complex compounds. Do not form complex compounds. Next, they readily lose electrons and they are good reducing agents. As they are metals, they are good reducing agents. Alloys of lanthanides with iron are called as Mixed metals. This is called not Mixed metals, it is called Mixed metal. What is mixed metal means? It is an alloy which consisting of iron with lanthanides. iron with lutetium, iron with lanthanides, any lanthanides is called as mixed metal. What is mixed metal? They ask here. CH is not been printed, so please note it down. Next, color. Many trivalent lanthanides. Trivalent means their valence is 3. Lanthanide ions are colored both in solid state and in aqueous solution due to FF electron transition. Why the lanthanides are colored? Due to FF transition. Why the D block elements are colored? Due to DD transition. In the same way here, F block elements are colored due to FF electron transition. The color exhibited depends upon the number of unpaired electrons in the 4f orbitals. The ions often with 4F-N configuration have similar color to ions having 4F14-N configuration. Very, very important point here. So they have similar colors. That is 4F-N or 4F14-N. If the values are same, then for example, lanthanide is having 4F0, 4F14 are colorless. 4F14 or 4F0 are colorless. If they do not have unpaired electrons, they are completely filled orbital, completely filled electrons, they are said to be colorless. This already we know in D block elements, we have seen that. Same here also we are following. So 4F0, 4F14 are colorless and remaining are colored. So that's why we can say most of the lanthanides are colored. Magnetic properties. In tripositive lanthanide ions, the number of unpaired electrons increases from lanthanum to gadolinium 0 to 7 and then decreases from lutetium 7 to 0. So lanthanum and lutetium are diamagnetic because lanthanum is 4F0 and lutetium is 4F14. So that's why they are called as diamagnetic because they do not have unpaired electrons. While other tripositive lanthanide ions are paramagnetic. Tripositive means plus the state. So except neodymium is the most paramagnetic lanthanide. Cerium plus 4 and ytterbium plus 2 are also diamagnetic. So if they're asking about paramagnetic or diamagnetic, simply you have to find unpaired electrons. If the ion or the substance containing unpaired electrons, we can say contains unpaired electrons, we can say it is paramagnetic. If the ions containing no unpaired electrons or completely filled electrons, we can say it is called as diamagnetic. So in lanthanides, we have only two substances which are diamagnetic. One is La plus 3 and there is Lu plus 3. So La plus 3, that is lanthanum plus 3 because it has 4F0 configuration, and lutetium plus 3 because it has, after losing 3 electrons, it becomes 4F14, completely filled. So in this number of unpaired electrons is 0. So that's why they are said to be diamagnetic. Diamagnetic. So please note down this sentence in your classwork. So only two ions in lanthanides are diamagnetic. What are those? Lutetium plus 3, lanthanum plus 3 are said to be diamagnetic. Remaining all paramagnetic except cerium plus 4 and ytterbium Yb plus 2 are also diamagnetic because of their 4F0 configuration and 4F14 configuration. So cerium plus 4 by ytterbium plus 2. These two are also diamagnetic because this is having 4F0 and this becomes 4F14. So all are completely paired. So that's why it is also diamagnetic. So that's why to know whether it is paramagnetic or diamagnetic, compulsory you should know the electronic configuration. Once if you know the electronic configuration, easily you can identify which is diamagnetic, which is paramagnetic. Next continuation, chemical reactivity. As these are very reactive metals like alkaline earth metals, the metals combine with hydrogen readily when gently heated in the gas. They form carbides and liberate hydrogen gas from dilute acids. They form carbides and liberate hydrogen gas from dilute acids. So lanthanide metal, here we have given a beautiful flow chart so that easily you can understand. So lanthanide metal, any metal you can take with sulfide, it forms sulfide. Formula is what? M2S3. For example, if you see here, lanthanide. So for example, you can take cerium plus hydrogen sulfide, sorry, sulfur. So 2 moles of cerium plus 3 moles of sulfur, it forms CuM, that is Ce2S3. Cu2S3. Like that, with acids, you can take any lutetium on reaction with HCl, it forms hydrogen gas. So with acid, it liberates hydrogen gas. With sulfur, it forms lanthanide sulfides. With halogens, it forms lanthanide halides. That is LnCl3, LaCl3, LuCl3, SmCl3. So any lanthanide with plus this state, it will form. Next, with water, it forms hydroxides. With carbon, it forms carbides, Mc2, that is lanthanide carbide. And with nitrogen, it forms nitrides. And with oxygen, it forms oxides. So all these reactions are very important. So flow charts. So you please take this flow chart immediately in your classwork and write it down. It's very, very important. So this is about chemical reactivity of lanthanides. These are very reactive metals like alkaline earth metals. The metals combine with hydrogen when gently heated in the gas. They form carbides and liberate hydrogen from dilute acids. Next continuation. Uses. Lanthanides are commonly used as production of alloy steels, as I told you. Lanthanides with iron, they are called as misty metal. Production of alloy steels for plates and pipes. A well-known alloy is misty metal, which consisting of lanthanide metal 95% and iron 5%, and traces of sulfur, carbon, calcium, and aluminium. It is used in gas lighters, flame-throwing tanks, toys, tank, and tracer bullets as well as in shells. Very, very important. So this is called uses of lanthanides. It is used as misty metal. So it is an alloy which consisting of 95% lanthanide metal and 5% iron metal. This misty metal composition they will ask in the entrance exam. So misty metal consisting of 95% lanthanide metal and 5% iron, along with traces of sulfur, carbon, calcium, and aluminium. Mixed oxides of lanthanides are used as catalysts in petroleum cracking. Petroleum cracking means burning of petrol. Cracking means burning. So when in the burning of petrol, these mixed oxides of lanthanides are used as catalysts. Catalysts. Some oxides are used as phosphorus in television screens and similarly fluorescent surfaces. Fluorescent means here lightning surfaces. Next, we have after finishing lanthanides, same we'll study about actinoids also. So it's very, very small chapter, but very important also. You'll get one question from lanthanides and actinides. Actinides are the elements in which the differentiating electron enters into 5F subshell of anti-penultimate shell. All actinides are radioactive, very, very important. The elements which come after uranium and hence they are called as trans-uranium elements. These elements will come after uranium because their atomic numbers ranges from more than 89 to 114. So that's why trans-uranium elements, as they are coming after uranium, uranium atomic number is 92. So that's why they are called as trans-uranium elements. The general electronic configuration of actinoids is 7s2, 60 0 1 0 to 1, 5f 1 to 14. Here 4f will go and 5f will come. The electronic configuration of actinoids and the ions in plus 3 oxygen state is given below, just like same. And here actinium is not a lanthanide. Apart from actinium, all that is from thorium to lawrencium, all are that is 92, 104, 103, 92, 104, 103. These elements are called as actinoids, and this is not actinoid, but due to its similarity, it's placed in this group. So first C61, 7s2, 5f0. So here also 5f0. So actinium plus 3 is colorless. We can say actinium plus 3 is colorless because it has n value 0. That is magnetic moment n is equal to 0. That is number of unpaired electrons is 0. Same with thorium. Next, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. These are the elements of actinoids, and in this also we have unusual stability, that is 5F7, 5F7, that is called americium, QEM. Please note down these elements in your classwork. These two, and again last two, that is nobelium and lawrencium. These are having unusual stability due to half-filled and completely filled F orbitals. 5F7, 5F7, and here 5F14, 5F14, 7s2, 7s2, 61, and 5F14. So this is colorless. This is colorless, and even this is also colorless, we can say. So nobelium, lawrencium, americium, QEM, and actinium. All these five elements are important. Remaining are also important. But the thing is, due to this half filled and complete filled, definitely they'll ask about half filled, complete filled, and even they'll ask about diamagnetic and paramagnetic, which is said to be diamagnetic now here. Actinium plus 3, AC plus 3 is diamagnetic, we can say. And next we have, if you remove 3 electrons from this, no, it is not diamagnetic. And if you remove 3 electrons from this, no. And here, if you remove 3 electrons from this, 5F14, so lawrencium plus 3 is diamagnetic, Lr plus 3 is diamagnetic. And next we have, after removing 3 electrons, yes, only these two are diamagnetic, remaining are all paramagnetic. These two are diamagnetic because no unpaired electrons. So that's why they are said to be diamagnetic. So please note down these 4 elements: americium, QEM, nobelium, lawrencium with atomic numbers. And as these elements are after uranium, so that's why we can say it is called as trans-uranium elements. And the first actinoid is thorium. It is not actinium. We'll say it is thorium. So 90 to 103, it is 14 elements. So these are all coming to 6s, 5F series. So this table is very important. Please note down. Next, ionic sizes. There is gradual decrease in the size of atoms or M+3 ions across the series due to actinide contraction. We'll call this as actinide contraction, which is similar to lanthanide contraction. And that is actinide contraction means due to poor shielding effect of 5F orbitals. Here we'll say due to poor shielding effect of, here I'm writing, you note down in your classwork, due to poor shielding effect of 5F electrons, 5F orbital, the electrons in 7s orbitals will come closer to nucleus, due to which what happens, they form, the size becomes smaller. That is element size, atomic size contracts. This is called as actinide contraction. Lanthanide means 4F orbitals and actinide means 5F orbitals. That is the only difference. But the property is similar. Next continuation. What are the common oxidation states of actinoids? Actinoids shows a range of oxidation states which is due to comparable energies of 5F, 6D, and 7s orbitals. The common oxidation states of actinoids is +3. This oxidation state becomes increasingly more stable as the atomic number increases. So they'll ask based on this, which of the following are more stable? So they'll ask based on TH +3, lawrencium +3, and americium +3. So which is more stable? As we go down the group, what happens? Increasing more stable as the atomic number increases. So answer will be decreasing order, Lr +3, Am +3, stable than, more stable than americium +3, more stable than thorium +3. Until and unless if you don't know the atomic numbers, you cannot write, because the atomic number of thorium is 90, lawrencium is 103, and americium is somewhere between 90 to 103, that is now 96. So that's why you should know the atomic numbers or at least order. The highest oxidation states in this actinides is +7, which will be shown by Np and Pa, protactinium and Np. It is unstable highest oxidation state is +2, +6 shown by uranium. Unstable highest stable oxidation state is +6. So usually they are stable at +3. That's why all the elements in this is important because they'll ask questions based on this. Next, general characteristics and comparison of with lanthanides. General characteristics and comparison with lanthanides. The actinoid metals are silvery in appearance but display a variety of structures. This is due to irregularities in metallic radii, which are far greater than lanthanoids. The actinoids are highly reactive metals. These are highly reactive metals than lanthanides. HCl attacks all metals but are slightly affected by nitric acid due to formation of protective oxide layers. As the actinides have protective oxide layers on the surface of actinoids, nitric acid will have the minimum effect, whereas HCl can attack all the elements. The magnetic properties of the actinides are more complex than those of lanthanides. So it is more complex than those of lanthanides. Next, the 5f electrons are effectively shielded from nuclear charge than 4f electrons of the corresponding lanthanides. Since the outer electrons are less firmly held, they are available for bonding in the actinoids. That's why actinoids are more reactive than lanthanoids. Actinoids are more reactive than lanthanides because the 5f electron will have less shielding effect. It will effectively shield from nuclear charge. Ionization enthalpies of actinides are lower than lanthanides because they are having bigger atomic number. Automatically, the valence electron will be far away from the nucleus. So that's why lanthanides ionization enthalpy is greater than actinides ionization enthalpy. Or you can say actinides ionization enthalpy is lesser than lanthanides due to atomic size or atomic number. Most ions of actinides are colored and possess greater tendency for complex formation. These compounds are more basic than lanthanide compounds. So lanthanides are more basic than, sorry, actinoids are more basic than lanthanoids. So this statement is very important. So based on these statements only, they can frame many questions. That's why it's very important to know each and every statement in inorganic chemistry because they'll ask based on this knowledge-based question only. All the known actinide metals are highly electropositive. They have high melting and boiling points. As they are metals, they have high melting points and boiling points. They do not follow regular gradation of melting or boiling points with increase in atomic number. Actinides are paramagnetic due to the presence of unpaired electrons. All the actinides are radioactive in nature, very important. The size of atom or cation decreases regularly along the actinide series. As they are radioactive, their studies are separately studied because once they exposed to air, they emit alpha, beta, gamma radiations. That's why these are less reactive because not reactive also you can say they are radioactive. So that's why these are separated in nuclear chemistry. This decrease in ionic radii with increase in atomic number is called as actinide contraction. This is due to poor shielding effect of 5 electrons. But however, the shielding effect, the 4f electrons is having less shielding. That is very poor shielding effect when compared to 5f. That's why lanthanide contraction is more than actinide contraction. The contraction of element is in lanthanides is more when compared to actinides because of poor shielding effect of 4f than 5f. Both show dominant oxygen state of +3 because lanthanides also will show +3, actinides also will show +3. Both are electropositive and act as strong reducing agents. Cations with unpaired electrons are paramagnetic in both of them. Most of the cations of lanthanides and actinides are colored due to unpaired electrons and paramagnetic. Both of them show a steady decrease in the ionic radii along the series. So almost similar properties. Next, in what way they are different? Besides oxygen state of +3, lanthanides will show +4 and +3. in case of certain elements. Plus 4 and plus 3. Actually, it is not plus 3. It should be plus 2. Because we have seen samarium Sm plus 2, ytterbium plus 2. So like that. Besides oxygen state of plus 3, some actinides will show plus 4, plus 5, and plus 6 oxygen state in case of certain elements. They have like tendency to form complex formation, and they have stronger tendency to form complex formation due to its high atomic size. So these are the main points of differences between lanthanides and actinides. Except promethium, they are non-radioactive. All are radioactive. So only a radioactive element in 4F series is, that is lanthanides, is promethium. This point they will definitely ask. Promethium is the only radioactive element in lanthanide. In lanthanides. Whereas in actinides, all are radioactive. Oxides and hydroxides are less basic. Oxides and hydroxides are more basic. Next continuation. Now let us see questions. What is the general trend of the ionization enthalpies of the lanthanides? General trend of ionization enthalpies of lanthanides means here I am writing the answer. So the ionization enthalpy, first ionization enthalpy and second ionization enthalpy was small when compared to third ionization energy because of its configuration in lanthanides. In lanthanides. But if you see from left to right, as atomic number increases, ionization energy decreases. Ionization energy decreases due to decrease in atomic size, decrease in atomic size. From in lanthanides. So this is the answer. This is the only answer. So continuation. Next. Among the lanthanides, cerium-3 can be easily oxidized to cerium-4, atomic number cerium-58. Why? Because cerium plus 3 is reductant and cerium plus 4 is oxidant. Please note down in your classwork answers. Next question. Why do zirconium, hafnium, niobium, tantalum exhibit similar properties? Because of their similar atomic sizes, similar ionic sizes, similar atomic or ionic sizes due to lanthanide contraction. Due to lanthanide contraction. MCQs we'll be doing in the next session. Meanwhile, we are doing only theoretical questions here. So why do zirconium and hafnium or niobium and tantalum exhibit similar properties? Because due to their similar atomic or ionic sizes due to lanthanide contraction. Next continuation. Which of the two, lanthanum hydroxide or lutetium hydroxide, is more basic and why? As we move from left to right, basic character decreases. Basic character decreases from lanthanum to lutetium. Next, why are samarium plus 2, europium plus 2, YB plus 2 ions in solution good reducing agents, but in aqueous solution, Ce plus 4 is a good oxidizing agent. Ce plus 4 is a good oxidizing agent, and samarium plus 2, europium plus 2, ytterbium plus 2 are ions in solution good reducing agents because they have half filled. That is samarium plus 2, europium plus 2, and ytterbium plus 2. They have half filled or completely filled f orbitals. Completely filled f orbitals, due to which they are good reducing agents, and this is good oxidizing agent because it is incompletely filled f orbital. Incomplete f orbital. You can see the electronic configuration of all these four elements 1, 2, 3, and 4. Then you can get the answer easily. Next question. Question number 6. What are the different oxidation states exhibited by the lanthanides? Only the exhibits plus 3 state. All lanthanides exhibits lanthanides. Common oxidation state is plus 3. Apart from this, they exhibit plus 2 and plus 4 also. Plus 2 in case of samarium plus 2, ytterbium plus 2, plus 4 in case of cerium plus 4. So mostly they exhibit plus 3 state. Next question. How would you account for the fact that actinoids exhibit a larger number of oxygen states than corresponding lanthanides because of less shielding effect? Less shielding effect, we can say, less in case of shielding effect, and more in atomic size and ionic size. More in atomic size and ionic size. Hence, they are able to form, and due to availability of F electrons, due to availability of F electrons, they can form complex compounds than corresponding lanthanides. Please note down this answer. How would you account for the fact that actinoids exhibit a larger number of oxidation states than the corresponding lanthanides? Because the shielding effect is shown in lanthanides is more when compared to actinides. So that's why in actinides, the size is also bigger than lanthanides and ionic size and atomic size. So that's why due to the availability of F electrons, we can say actinides will form larger number of oxidation states when compared to lanthanides. I hope it is clear. Next continuation. So these are the important questions based on F block elements. Which is the last element in the series of actinoids? Write the possible electronic configuration of this. Comment on the possible oxygen state of this element. So lutetium. Lutetium is the last element of actinoids. You can see that that's what I told. So it has 5F14. The configuration is what? It is plus 3 state, and configuration is 5F14. All are completely filled. So you can see the last series of actinoids, and you can comment on the possible oxygen state of the element is only plus 3. Next. So This is about lanthanides and actinides. Some questions also we have discussed. The next session we'll discuss more questions on lanthanides and actinoids. And with this, I'm ending this session. Thank you all.